Okay, I am now on your clock. Let's get going. So we're working on the last major topic of Rob 501, some real analysis. And the main thing we're after is to understand convergence of algorithms. So when you have iterative methods to compute solutions to equations, it's wonderful when you can write down a closed form solution to something, but it's not the norm. So we're developing the framework so we can analyze convergence and understand what that means. So we start by putting ourselves in a vector space where we can know what distance means. So we're doing norm spaces. We could do metric spaces, but this is already abstract enough for us. So we define the distance between 2 points as the norm of their difference. And if we have a subset, just like when we were doing best approximation problems, the distance from a point to a set is the infimum over all of the points in the set, distance x to y. So we're going to use the notion of distance to characterize open sets and closed sets, basic topology. And then that will set us up for doing sequences, and that will set us up for the fun stuff. So to get started on defining open sets, we first define a very basic open set that we call an open ball. So the open ball of radius a about a point x0 is the set of all points in our norm space that are strictly less than a in distance from x0. So the distance from x to x0 strictly less than a. And it's that strict inequality that means it does not include the boundary of points that are exactly a away that makes it open. Okay, so that's really what's going on there. We use this notation tilde for the set complement. So the complement of a set is all the points in X such that X are not in A. If A is all of X, then that complement would be the empty set. And if A were the empty set, that complement would be all of X. So those both are fine. And so if this is A, then not A is everything that's not in A. And if B is over here, so B is in the complement of A, then that means that B intersected with A is the empty set. So those two things are equivalent. B intersected with A is empty, means B is contained in the complement of A. And that's going to be part of our mental gymnastics when we characterize open sets and closed sets with distance. Okay, so here's some crazy set S that has some filled in parts and some streamers and some disjoint points and stuff. And here's a point X that is in the complement of S, because S is everything in blue. So if you want to include this as being part of S, that's fine with me too, okay? And so here's a ball of radius epsilon about X, where epsilon is positive. And so once again, ball of radius epsilon about X intersected with S is the empty set if and only if the ball of radius epsilon about X is contained in the complement of S. So that's the same thing as B intersected with A is the empty set. Okay. And so this is how we were using that at the end of class on Thursday when we introduced our distance, and we tried to characterize it in terms of these open balls. And we're looking at when is the distance of a point to a set equal to 0? Well, distance 0 means that the infimum over all points in y of the norm x minus y is 0. So that means no matter how small my approximation error, I can find a point in S such that the distance from x to y is less than epsilon. And so that means no matter how small of an epsilon I take, if I take an open ball about that point, it has to intersect S in a non-empty way. So it must contain a point in S. So this empty set, this set being non-empty means there is something in here and something in here. So something in here means it's in the ball of radius epsilon of x, so it's within epsilon of x, and then y is in S. Okay, so those two things are the same. So the distance from x to S is 0 if every open ball about x intersects S in a non-empty way. Those two things are equivalent. And so the opposite of the distance being 0 is the distance being positive, and that's simply because it's impossible for the distance to be negative. So the complement or the negation of this statement is strictly greater than 0. And so we negate this statement, and when we negate the for every, we have there exists an epsilon greater than 0, such that the ball of radius epsilon about x intersected with S is in fact equal to the empty set. And if the ball of radius epsilon about S intersected with S is empty, that means that ball is contained in the complement of S. So the distance from x to S is positive means I can put a ball of radius epsilon about x and be in the complement. And that's that picture here. All those things are equivalent. Mic is not on, or it's rubbing? Rubbing. Mechanical solution, not an electrical one. How about that? Okay, so here I can put an open ball about x and be contained in the complement. That's the same thing as the distance from x to S is positive. And if the x was sitting, say, here, then no matter how small the ball is, I would intersect it with x, and then the distance from x to S would be 0. So these are the two really important things we have about distance to S is 0. If no matter how close, how small I make my ball, I always intersect it with S in a non-empty way. And the distance from x to S is positive. I can bound x away from S by an open ball. Those are good. Too easy. It's kind of obvious once you say it 10 times, you almost believe it. Maybe, okay. Okay, so today we're doing open sets and closed sets. All with the goal of understanding sequences, convergence, so we understand algorithms. Okay. So definition, we'll leave it with that. So P contained in X, subset A. A point in P is an interior point if there exists epsilon greater than 0, so I can put an open ball about P and stay in P. That's an interior point. Get that? Put a ball about it. So something in here that looks like an interior point, I can put a ball around it. Something here on the edge, I can't put a ball around it and stay in there, okay? That's the difference, geometrically. B, the interior of P, so we put P with a little circle above the top. Set of all P in P. P is an interior point. Interior point is the interior of P. Okay. So just going back to this picture, this would not be an interior point because I put a little ball around it. I'm sticking outside of P no matter how small it is, okay? This would not be an interior point. Somehow in here it looks like I've drawn it like it's an interior point, okay? So that's the interior of the set. The inside, if you wish. Okay, so just a little remark, and let's see how we can characterize that with distance. Okay, so the interior of P, the set of all P in P such that there exists epsilon greater than 0. The ball of radius epsilon about P is strictly contained in P. So that's the definition. Okay, so the interior of P is all the interior points. So those are points I can put an open ball around it. Now if I can put an open ball around P, what do I know about the distance of this point to the complement of P? It's positive, okay? So this is our mental gymnastics. It's the set of all points P in P. It's just the distance from P to the complement of P, strictly greater than 0. Now, I'm going to rewrite it like this. Okay, I'll write down why this is true. Okay, so this is that picture that we talked about summarizing from the end that you said you're all really good about. If I can put a ball around something, then its distance to the complement of the set is positive. Those are if and only if. Okay, why can I replace P and P with arbitrary X and X? Well, X is P union complement of P, right? If X is in the complement of P, what is the distance of X to the complement of P? 0. So it's not in there, okay? So they're exactly the same sets, okay? Okay, and that's true because if X is an element of the complement of P, then the distance from X to the complement of P is certainly 0, because the distance of X from itself is 0. Okay? So we can write down interior of P equals set of all X in X, distance from X to the complement of P is positive. Okay, so that's the interior of the set. It could be empty, could be everything, it could be a lot. Definition. P is open if its interior is equal to the whole set. Okay, so that's the definition. A set is open when every one of its points is an interior point. So no boundary points, no boundary points. That's when it's open. So the open ball is open if it doesn't include the boundary points, okay? We haven't defined boundary, but I think you have an intuitive notion. Okay, so conclusion. P is open if and only if P is equal to set of all x and x, distance from x to the complement of P is positive. Okay, interior of P, set of all points in x that are positive distance away from the complement. Okay, write that down. We're going to go back to our little picture just to see if geometrically you're good with this. Let's go back to our picture, okay? This is an interior point. Here's the complement of P. Its distance to the complement is positive because I can put a ball here of radius epsilon. Is this in the interior of P? No, here's the complement. Don't reach up, you rub, okay? Only reach with this arm. If you put a point here, is it in the interior? No. If I put a ball around it, it always intersects the complement no matter how small the ball is. So the distance of this point to the complement of P, of S in this case, is 0. So it's not in the interior, okay? Something's in the interior if it is bounded away by a positive distance from the complement of the set. Here, the complement of the set is too close. Here, the complement of the set is positive distance away. So that's the notion of interior and how we can characterize it with distance. So, okay, let's just do a few examples. They're almost too trivial, but we can do the calculations quickly. So I'll take x equals r, and the norm is just the absolute value. Okay, so the real numbers is my set of vectors, and it's the field, of course, and the norm on that is the standard absolute value. So, question is, okay, so this is a little bit redundant. Is the open interval 0, 1 open, okay? Well, let's just check it by the definitions, okay? Let's just check it by the definitions. So, x is an element of P if and only if 0 is strictly less than x is strictly less than 1. So let me check it by, is x an element of P if and only if x is an interior point by the ball definition. So if I let epsilon be the minimum of x over 2 and 1 minus x over 2, okay, so that'll be a positive number because x is strictly bigger than 0 and is strictly less than 1. And divide by 2, it's still a positive number. Then we can check that the ball of radius epsilon about x is an element of P. Okay. That says x is in the interior of P. So P is indeed open. Okay, so what are we checking? Something is an interior point if I can put a ball around it and stay within the set. So there, I took a point, I produced the epsilon, hence it's an interior point, and since this was an arbitrary point in P, then P is open by the definition. P is open if it's equal to its interior. Okay, we're just checking that definition. Now I'm going to check the distance characterization, just to show the duality here. Okay, so let's check the distance part. So what is the complement of P? P is 0, 1, so the complement is going to be minus infinity, 0, union, 1, infinity. Okay, x is in P if and only if 0 is less than x, less than 1, just like we had before. So what is the distance from x so x is strictly bigger than 0. What is the distance of x to this part of the complement of P? It's just x, which is positive, okay? Everybody agree it's equal to x? X is like 0.04. The distance from 0.04 to 0, which is the closest point, is 0.04, okay? Now what's the distance from x, whoops, to here? Okay, so x is between here and here. What's the distance to this part of P, complement of P? It's 1 minus x, which is still positive, okay? Okay, so the distance from x to the complement of P then is the minimum of x and 1 minus x, which is still positive, because the minimum of two positive numbers is positive, okay? So x is in P if and only if the distance of x to the complement of P is positive. So x is in P if and only if the distance from x to the complement of P is positive. So okay, so let's see if this is making any kind of logical sense here. We defined a set to be open if all of the points are interior points, meaning I choose a point in here, I put a ball around it, I stay in this set. And then we've characterized that by distance to the complement, which seems totally worthless for the moment. I totally agree with you. There's no reason we should look at this characterization until we define what is a closed set, and then we'll see the duality going on here. Okay? So we can do it either way. And I'm just pointing out on this trivial example, we could check it by the definition, checking that each point in P is an interior point in P, or we could check it by the characterization, every point in P is a positive distance from the complement of P. Those are the same things. There'll be the same thing for you tomorrow, maybe? You'd be more clear, or no? Question? I don't want to be like, brutally saying you have to agree because I'm the professor and you're the student. Questions? Or does it just seem pretty obvious? Not seem obvious? It seem like something you can accept? Okay. We don't want to declare anything because that might ruin our Thanksgiving break. Okay, got it. Okay, so that's open sets. Definition. Once again, P contained in X, a subset. A. X is a closure point of P if for O, I don't know where that feature comes from, if for every epsilon greater than 0 there exists Y in P such that the distance from X to Y is strictly less than epsilon. i.e. distance of X to P is equal to 0. It's the same thing. So something is a closure point if I can approximate it arbitrarily well by elements of P. That's the definition of a closure point. These are points I can approximate arbitrarily well by points in P. So their distance to P is 0. Distance to P is 0. Okay. B. Closure of P, denoted P over bar, P closure, is P closure equals set of all X in X such that X is a closure point P so that's the set of all points in X such that the distance from X to P is equal to 0. Okay, so I can take a set and I can compute a larger set called its closure, which includes all of the points that are distance 0 from P. So if I take my open ball, the boundary is now in here because that's distance 0, okay? I close it up. Okay, and then definition. P is closed if the closure of P is actually equal to P. Okay, so I'm going to do another example, checking this. But let's look and see what we got. The closure of the set is the set of all points that are distance 0 from P. And the interior of a set is the set of all points that are a positive distance from the complement. So this condition is the negation of the other condition, is what we'll see. Okay? So we're going to have the result: a set is open if and only if its complement is closed. So they're opposite notions. Okay? If a set is open, its complement is closed. If a set is closed, its complement is open. And that follows from this distance characterization. That's why that's a useful thing to do. So that's where we're going. Let's do a little simple example of checking things about whether sets are closed or not, just like we did with open. And we'll do it with two different ways of doing the characterization. So. Example. So once again, our norm space is the reals, and the norm on that is the absolute value. Let's check that something that is the half open interval is not closed. Okay, so why would we suspect that that set is not closed? Well, is the point 1 in this set? No. What is the distance of the point 1 from this set? 0. Okay? You can arbitrarily approximate 1. Okay, so not closed, and that's because 1 is not an element of P, but the distance from 1 to P is equal to 0. What would be the closure of that set? Set of all points that I can approximate arbitrarily closely by elements of P. I don't want the half-open interval. I want the fully closed interval. Okay, so that's the closure of P. Now, here's a little more interesting one. Let's let P be the rational numbers. Okay, are the rational numbers closed? Are they open? Are they neither? Okay, so how would we check, for example, that this set is not closed? Can we find a number in the reals that is not a rational, but yet is distance 0 from that set? Well, you guys know something about the square root of 2. Though you'll totally deny it because it happened more than a month ago, right? And it wasn't on exam 1, so it didn't happen. Okay, square root of 2, you know, is not an element of P, but it does have a decimal expansion. Okay? Okay, then if you take the closure of P, you get, that's really how you get the real numbers, but we're not quite there yet. We'd have to get Cauchy sequences and all sorts of crazy things, but anyway, so that would be a set that is, it's not closed, and in fact, you can check it's not open either. It's neither. Okay. Okay, questions on the definition of a closed set? All the points, a set is closed if it contains all of its closure points, and that means the only points that are distance 0 from the set is the set itself. So, I don't know. Is this set closed? So if this is just a point, that's no problem. A point is closed, okay? Those points are closed. Here, yep, they're all distance 0 from the set, okay? So, unless there's something here getting closer, closer, and closer, and closer, and closer, and closer, and closer, a whole bunch of rational numbers piling up to maybe 1, 1 or something, that set looks like it's closed. Okay. Okay, so here's our big theorem for right now. Theorem. Let X be a normed space and P contained in X a subset. And P is open if and only if complement of P is closed. Okay. P open, complement, closed. Just by replacing P with its complement, you get the opposite. P closed if and only if its complement is open. So open sets and closed sets. The complement of an open set is closed, and the complement of a closed set is open. Okay, so let's just prove that with our distance and etc. characterizations, and then that'll see if we really can piece all this stuff together. Questions before we get going? Yes, please. Neither closed nor open?
Yeah, is it really?
No, but there's a term that we'll introduce for sets that are both closed and open. So, right, you set me up perfectly. They're called Clopen. Literally. I will write it down when we get to it, okay? You didn't expect that one, did you? No. Neither did I when it happened to me, okay? So, okay, so let's do the proof. See, real analysis can be fun. It can be amusing. It can be wild. Okay, so let's do this. P open if and only if the interior of P is all of P. That's the definition. So that's if and only if P equals the set of all X in X, such that the distance from X to the complement of P is positive. Okay, that's our characterization of the interior. So that's if and only if P is equal to the set of all X in X such that there exists epsilon greater than 0, and we have a ball of radius epsilon about x that intersects the complement of P, and we get the empty set. Okay? X is bounded away from the complement of P. So I can find some sufficiently small bound such that all the points that are near X do not intersect the complement of P. Okay? So that's if and only if P is equal to the complement of the set of all X and X. So the complement of this set would be things that no matter what epsilon is, I take the ball of radius epsilon about X and I intersect the complement of P, and it's not empty. Uh-huh. Okay, we good with this? P is equal to interior, so P is equal to set of all points that are a positive distance away from the complement. Positive distance, I can put a ball around X and I don't intersect the complement. Okay? And then the negation of this condition, so this is exactly the same thing. These are the set of all points that don't satisfy this. For every epsilon greater than 0, I take my ball about X, I intersect the complement, and I contain a point in the complement. Okay. It's the same thing. So I have P is open then if and only if the complement of P is equal to the complement of a complement, the set of all X and X, such that for every epsilon greater than 0, ball of radius epsilon about X intersected with the complement of P is not empty. Okay, so as long as P is open, all of these things are true. So as long as all the things are open, I complement this, I get the complement of a complement, so I get this. Now, what are all the points in X that are distance 0 from the complement of P? That's the closure of the complement of P. Okay? That's the set of all points that are distance 0 from the complement of P. Okay, so P is open if and only if the complement of P is closed. The complement of P is equal to its closure. Ta-da! Okay, so that's our big result on open sets and closed sets. And what you want to make note of is the characterization of open sets and closed sets via the notion of distance. Okay? So that's what allows you to tie the two things together, the notion of distance. Okay. Okay, so I promised I'd come back to this, so can a set be both closed and open? Okay. The answer is yes. Such sets are. Not everyone uses this, okay? Sometimes called Clopen. Okay? It's too funny to be true, but it's often true, okay? Not everybody uses that definition. Okay, but what are those sets? Okay? Well, let's take the whole norm space. Okay? Is it open? If I take a point in here, can I always put a ball around it and stay in there? Yes, okay. Is it closed? If I take a point in here and I put a ball around it, do I always intersect the complement, okay? And the answer is no. Okay, so this is closed and open. Okay. Does it contain its closure points? Yes. Okay, every set point in X that's distance 0 from X would be X itself, okay? I take a point in X and I ask what is its distance from a point X to the entire space? It's 0. Okay, so every point in it is a closure point. Every point is open. Now by convention, the empty set is both closed and open. And why do you use this convention? Because if a set is closed, its complement is open. And if a set is open, its complement is closed. Okay, so that's why we need to do by convention the empty set. Okay. Don't worry, I don't care about Clopen for the final exam. Okay. Now, here's some practice for when you get bored out of your mind, when your aunt and uncles have asked you for the 42nd time if you've learned more robotics this semester or something like that, okay? You can say, no, sorry, I've got to go do Professor Grizzle's crazy exercises. So exercises. Yep.
If you're like doing a proof and you end up that the complement of the set is the empty set, then you can just say that set is closed.
Yeah, so the only set where the complement is going to be the empty set is the entire vector space itself, or the entire norm space. Yeah. So those are the only two sets that are both open and closed. Yes. So this is as in X, the norm space. Yeah. Yeah. X equals entire normed space. Yeah. So the set X meaning the entire norm space. No, that's a good clarifying point. Okay, so here's the exercises. Arbitrary unions of open sets are open. finite intersections of open sets are open. Okay, you can have uncountably infinite unions of open sets and it stays open, but only in general finite intersections. And I'll give you an example that shows that. Okay, so it's really important when you look at intersections in general, if it's not finite, then it may no longer be open. Okay. Only finite intersections are guaranteed to be open. Yep.
Finite here, is that referring to the number of intersections?
Number of sets, yeah. Mm-hmm. Yeah, so you take as many open sets as you want and you look at their union, or you take a finite collection of open sets and you look at their intersection. Those are open. And then arbitrary intersections of closed sets are closed. Okay, and finite unions of closed sets are closed. They're not, I mean, suppose I take a point and it's in each of a finite number of open sets. If it's in the open set, I can put a ball about it of radius epsilon. So just index that epsilon as 1, 2, 3, 4, capital N, okay? Now I do the intersection. Can you give me an epsilon so that it stays in there? The biggest one might spill out, right? But the smallest one, so take the minimum. Okay, so take the minimum over that. And then here, if something is in one of the sets, it's in the union. So just use the fact that the individual, if something's in the union, then it's in one of the sets. You can put a ball in it, then it's in the whole union. Okay, so. And the other ones are exactly the same, or you can use De Morgan's laws about how you relate complements of unions to intersections. Okay. So here's an example. Let's do it. This is important. I want red. Oh, example of a countably infinite intersection of open sets that is not open, okay? So I'm going to take a whole bunch of open sets, an infinite number of them, but countable, intersect them, and have it mess up. Okay? So I'm just going to show you that the finite thing is important. That's all I'm doing here. Okay, so here's how we do it. for every n greater than 1, define an equals 1 plus 1 over n. Okay? And just for the record, we'll write that as n plus 1 over n. Guess what? The closed set minus 1, 1 is contained in minus an for every n bigger than or equal to 1. Because no matter what n is, this is strictly bigger than 1. So even if I put open intervals, this guy is always in there, and this guy is always in there. You see how those things fit? Everybody's good with that? Okay. Now, suppose the magnitude of x is strictly greater than 1. Then there exists some finite k such that k plus 1 over k is strictly less than the absolute value of x. Everybody good with that? X is 1.01, take this to be a million, then 1,000,001 over 1,000,000, that's strictly less than 1.01, okay? So I can always exclude it, okay? So if X is in here, that implies X is not in minus AK. So now I take intersection n equals 1 to infinity minus an. So it's an intersection of an infinite number of open sets. And I get this. How do I get this? Well, if something's in the complement of this, then the magnitude of it is bigger than 1, and then it's outside of one of these sets eventually, so it's excluded from the intersection when n gets sufficiently large. Okay? So the intersection is closed. So here's open. Infinite number of intersections this is not open, okay? That's the only thing we care. It's not open. Okay, so if that was too fast, you can go through and check all the calculations. So the key thing on your exercises, once a set is open, you can take an uncountably infinite number of unions of those things and they stay open, but only a finite number of intersections in general. When sets are closed, you can intersect as many of them as you want and they stay closed, but also only a finite number of unions. I mean, the real numbers are the union n equals 1 to infinity of the closed intervals minus n n, okay? You get every real number, okay? So this set is open, and these are closed, and there is a whole bunch of unions, okay? So now, it's still closed, but it's okay. It's also open, so it's not necessarily, so that'll work. Just for fun, what is the boundary of a set? Okay. Let's go back to our picture, this crazy thing. Okay, let's just start with an open ball. The boundary you would want to be this exact point where the radius is constant. That's what you want to be the boundary. How would you characterize that then? Well, this is part of the closure of my open ball, but it's also part of the closure of the complement of the set. So you can write down the boundary as the closure of the set intersected with the closure of its complement. Does that work? Closure of the set, okay. What do I want to be the boundary? Well, I want to get rid of all these things that are in the interior, okay. So intersected with the closure of the complement. So that's, okay, so the symbol one uses, I'm not very good at making it, it's that funny delta. It's the closure of P intersected with the closure of the complement, that's the definition. And the exercise is closure of P is, the boundary of P is the closure of P, take away the interior of P. So it's the set of all points X in the closure of P such that X is not an element of the interior. Okay, so that's kind of the geometry of norm spaces in terms of open sets, closed sets, and if you want, the boundary. Okay? Yep.
So does every set
Yes, because every set has a closure. Does every set have a boundary is the question. And the answer is yes, because every set has a closure. Every set has a complement, and we can calculate the closure of that and then do the intersection. Every set has a closure. Every set has an interior. We can take it away. Now, it is possible that the boundary is the empty set. Maybe that was your question. Yeah, so it still exists, but it's the empty set. So the boundary of the entire space would be the empty set, okay?
Could we just write instead maybe that the boundary is the closure P intersected with, just not necessarily the closure of
Complement.
complement of P, but just the complement, the intersection of those two. Does that also work, or?
No, because the intersection, the question was, do I need the closure on this second part? And the thing is, the complement of P, if P is closed, then P is already equal to itself, and P intersected with the complement would be the empty set.
Okay.
Yeah. So you need to have the closure so that you get the whole thing. So take P is the ball of radius A about 0. And you want the boundary of P to be the set of all x in X such that the norm of X is equal to A. So what happens here? We took the closure, and if we intersected with the complement in this case, it would all work just fine in your case, okay? Now I take P is the closure of this set, and then it doesn't work anymore. Because the complement is everything whose norm is strictly greater than A, not greater than or equal, and then this becomes the empty set. Yeah, so. From a question in class, not something that I want you guys to know. Question in class. Okay? Cool. That's the boundary. Let's do a tiny bit of sequences, just to get a little bit of juices flowing. Something kind of fun. Okay. Okay, so all of this crazy math is aimed at being able to analyze problems like this. I want the solution to the equation h of x equals 0. I think we're at the row number 5. You want to give me the answer, please? Yeah, okay. The problem is, as soon as you get polynomials, monomials, and trigonometric functions, you just can't write down the answer, right? So how are you going to find it? You're going to iterate, you hope. Okay. You hope you can find an iterative approach to it. So this is Newton's algorithm. Let me just write it down very quickly. We'll study it a little bit later. Newton's algorithm is xk plus 1 is xk minus dh by dx evaluated at xk inverse times h of xk. So I've just posted a handout on it. You don't have to read it yet. We haven't quite gotten to it. Okay. That's called Newton's algorithm. we start out with a really intelligent guess, 7, 8, 9, 10, okay? Super intelligent, okay? Just to make a point, I run Newton's algorithm, and after 16 iterations, I get this answer. And this is H. And when I plug it back in, I get H of X is 10 to the minus 39, 10 to the minus 39, 10 to the minus 38, 10 to the minus 32. Is that good enough? Pretty good, okay? You happy with that? Okay, so. So this is a sequence. I start out with some arbitrary point. Maybe if I'm going to index them by the counting numbers, this would be x1 instead of x0, but who cares? It's the difference between MATLAB and C, right? Okay, so I get a sequence of approximations, I hope, to the answer. Now what I want to be able to do is to analyze, does this thing actually converge to a solution of this equation? Okay, so that's the whole notion of sequences. Okay, so I'll keep it in red, given. Given X, but a normed space. Definition, a set of vectors x sub n indexed by the counting numbers is called a sequence. Okay, so that's a sequence. Sometimes you see an alternative notation. They'll be put in curly brackets instead of the curved brackets, okay? So it's still a sequence, and it has to be indexed. It doesn't really matter that it's counting numbers, but it can't be the full integers. You can't go infinite in both directions. You could start at minus 400 million and go forward, that's fine, okay, because it's shifting. Okay, so you can only go infinite in one direction, and the counting numbers make sure that that's what happens, okay? So that's why we don't say index by the integers, because they go negative in both directions. They go infinite in both directions. Okay. So this is what we're really after, definition. A SEQ ENCE converges to the point X in X. I'm going to give that sequence a name, sorry, XN. If for every approximation error that's positive, no matter how small, I can find a finite number. As I make that number epsilon smaller, maybe my n has to get bigger. Such that for every index that's bigger than or equal to n, all of the points are within epsilon of x. equals limit n goes to infinity of xn. Or we'll simply write xn goes to x. Or xn goes to x as n goes to infinity. You see lots of different notations, okay? Okay, so this is wonderful, but the only way I can check that a sequence converges with this definition is if I know the answer to my problem, okay? Huh. I want to check that this converges to this, and the only way to do it with the definition is I have to have the answer in my pocket, and I have to check that these things are getting closer and closer as k gets bigger and bigger. That's a problem, right? How do I check that a sequence converges? Well, it converges to a point if everything accumulates to that point if I go sufficiently far. Make this 1 over Avogadro's number, and then this is 10 to Avogadro's number. And anything beyond that, I'm within that really, really close approximation. But to check it, I have to have the answer in my hand. And for engineers, that doesn't work. Okay, so we come back, we're going to have some real fun. We'll get beyond all of this just kind of boring, a set is open, if I can put balls in there, and a sequence converges, if it gets close, we're going to start having a more intellectual discussion about how we can characterize, how we can characterize convergence of a sequence, and how we can check properties of an algorithm that will guarantee that when we iterate it, the sequence will have an answer, and what equation that answer will satisfy. That's what we're after. That's what we're after. We're engineers. Sorry, question.
That algorithm you're showing us before, is that assuming that there is a solution, and then if there isn't, are you just gonna find the closest one? And then does it depend on the actual functions that you're trying to approximate whether it's actually gonna work?
So the question is, this Newton's algorithm, what can I tell you about it? So we've got a whole handout that we'll actually go through, okay? All I'm doing is using it to motivate the fact that we have lots of problems of engineers that we can't write down a closed form solution like the normal equations, okay? The normal equations. We've done so many things where we write down the answer in terms of matrices, done. There's lots of problems that don't satisfy that. How do you analyze them? That's all I want you to get out of this picture for today. And then we'll spend a little bit of time on this algorithm because it's an example of a contraction mapping. Yep, question? Okay. What if my equation were h of x equals sine of x? Is there one solution? Yes, there is one, but there's also two. There's also three. There's also four. Okay, there's a whole bunch of solutions, okay? So, can this algorithm be global for all nonlinear equations? No. Okay, sine of x is a good thing. I can take x squared minus 1. That's another example. I can do Newton's algorithm, but I can get two answers, plus 1 and minus 1. Okay, so yes, it's not global, but we'll have conditions that you can check whether you do get global or not, and things like that. So Newton's algorithm for us is a motivated way that we can see sequences and little finite dimensional problems that we care about. And it's cool. Wow, I haven't had that much interest in Newton's algorithm in at least 2 years, okay? You guys are great. So I hope everybody has a wonderful break. And I'll see you back in a week.